Hello, I'm Dr. N.B. Hulle. In this video, we'll try to understand analysis of transient response of RC series circuit, that is the first order system. In this case, we will divide this total topic into the three parts. In the first part, we will discuss the transient response of RC series circuit with source with zero initial condition. Second part deals with source-free RC series circuit, and third part we will try to understand source-driven RC series circuit with some initial conditions. To begin with the first part. In this case, for the transient response of the first order system, we have considered this RC series circuit. In this case, the switch is in the off state for a long time and the steady state was reached. At t is equal to 0, the switch is closed and we will try to understand its behavior in that particular period, which is the transient period. As usual, we will divide this working of the circuit into the two parts, that is analysis of the circuit for t less than 0. For t less than 0, the switch is open and the steady state was reached. That's why in the steady state this capacitor acts as open circuit. That's why it is open circuit. This resistor will be the same as it is, and from this circuit we will find out Vc of 0 minus, which is equal to Vc of 0 plus, which is equal to 0 volt, is the initial condition of this network. Then we'll try to analyze the second part, that is behavior of the circuit t is greater than 0. In this case, we will apply the KVL to this circuit and we will prepare its equation. For that case, we have taken the direction of the current, which is clockwise. In that case, this will be the positive terminal of the battery. This is the negative, and this is the positive terminal, and this is the negative terminal, and here the positive and negative terminal of the battery. Now here in this case, we will apply the KVL to this circuit. We will start from this particular point. If we are traveling in the clockwise direction, negative to positive, this voltage is the plus value. Then positive to negative, which is minus, voltage across this resistance will be I of t into R. Then positive to negative, which is minus, Vc of t, that is voltage across this capacitor, is the Vc. Here this voltage across this capacitor is the Vc, or sometimes it can be mentioned as a Vc of t. But here we are aware of the current flowing through this capacitor or current flowing through the RC series circuit is given by the expression, that is I of t is equal to C into dB by dt, where V is the voltage across the capacitor. If we are substituting this value of the I of t in this equation number 1, then this voltage will be the V, this resistance R, it is as it is, and this I of t is replaced by differentiation of this Vc of t with respect to t minus this is Vc is equal to 0, because this I of t is nothing but C into dB by dt, which is C into, it is d Vc of t upon dt minus Vc, which is equal to 0. If we will simplify this equation, we are shifting these both terms on the next side, then V is equal to Rc dV by dt plus Vc. Now here we are separating the variables. We will separate the variables. We are shifting this Vc on this particular side. It will become V minus Vc, which is equal to Rc dVc of t upon dt. Now if we will shift this Vc of t on this side, then it will become dVc of t upon V minus Vc, which is equal to 1 upon Rc into t, which will be shown on the next slide in this way. Now here in this case, it is dVc of t upon V minus Vc, which is equal to dt upon Rc. Now we will integrate this equation on both sides. Integration of this first term, which is equal to integration of the second term. But here, if the differentiation of the denominator is available in the numerator, in that case log of denominator will be the integration of this particular term. For that particular case, we will modify this equation by multiplying by the negative sign or minus sign. This minus sign on both sides. Now here in this case, differentiation of this term is now available in the numerator, which is minus 1. That's why the log of denominator, which is V minus Vc, is the integration on the left hand side. Now here, that is 1 upon Rc is a constant and integration of the dt is t, and this minus sign is as it is plus some constant of integration, that is a k, and we will name this equation as equation number 2. Now here we are in a position to find out the value of this integration constant from the initial condition, which is at t is equal to 0, Vc of 0 minus, which is equal to Vc of 0 plus, which is equal to 0. If we will put this condition in the equation number 2, then we are able to get that value. Now here in this case, at t is equal to 0, this Vc of 0 minus is 0. That's why this Vc will become 0. This value is 0. That's why it is log of V. If this t is 0, then this term will be the 0 and plus k. That's why the integration constant from this equation is k is equal to log of v, and we will name this equation as equation number 3. Now we will substitute the equation number 3 in equation number 2, and we are able to find out the expression for voltage across the capacitor. Now here, if we are putting the equation number 3 in equation number 2, in this case log of v minus vc minus t upon rc is equal to plus k, and this value of the k is nothing but it is log of v, that is log to the base e of v. Then here we will make the adjustment in the term. We will shift this value on the this particular term on the left hand side, that is log of v minus vc minus log of v, which is equal to minus t upon rc. Log a minus b is nothing but it is log of a upon b, that is v minus vc upon v, which is equal to minus t upon rc. Now here, if we are taking the antilog on both sides, in that particular case this term will be the v minus vc, which is equal to e raised power of minus t upon rc. But here the time constant rc of the circuit is nothing but tau, and which is equal to rc, and in place of this rc, if we are putting its value as a tau, then expression will be v minus vc upon v, which is equal to e raised power of minus t by tau. Finally, if we will simplify this equation, we will get the term voltage across capacitor is equal to, or vc of t is equal to, or v minus v into e raised power of minus t by tau, which is equal to v in bracket 1 minus e raised power of minus t by tau. Now here, if we are trying to understand its behavior, in that particular case we will find out the two cases. At t is equal to 0, how will be this equation? How will be this equation? At t is equal to 0, this e raised to power of 0 term will become 1. 1 minus 1 is 0, is this vc of t will be 0. In this particular case, at t is equal to 0, this vc of t is 0. Now we will find out its second point, that is at t is equal to infinity, e raised to power of minus infinity is nothing but 0, and it is 1 minus 0 is 1, and 1 into v will be the v, means at t is equal to infinity, vc of t is nothing but its maximum value. Means here this is the maximum value at this instant, which is at t is equal to infinity. Then here this curve will be exponentially increasing curve. That's why here this is the charging of the capacitor expressed, that is vc of t is equal to v into 1 minus e raised to power of minus t by tau. And this is the expression for transient response of the RC series circuit with source and having its zero initial condition. Thank you for watching this particular video. Thanks a lot.